McCutcheon. I'm doing my PhD at the University of Bristol, where in the Centre for Quantum Photonics, where we in general study the quantum effects of really small systems on an optics bench, in particular bits of light. And quantum mechanics is really good at reproducing these effects, and we see loads of things that can't be explained in any way that traditional objects would in general behave. But although this formalism works in these systems where we can measure it and we can see it doing unusual things, like as to how it will behave in a cosmological scale, or how the universe might look in under this formalism, it's kind of still a very open question. There's a lot of there's even a conference on time happening in September in Zurich, and there's much kind of progression in this direction. So hopefully, if we can have a better understanding of how time kind of governs the dynamics of small systems, then we can see how it might be expressed on the universal level, and in particular what kind of dynamics we expect to be able to access from our minds, or how we might interact with the universe. Ideally, we could find this out. So before even touching on what quantum mechanics has to say about time, we had this age-old problem even before 100 years ago, when the first kind of industrial revolution in this period of mathematics, where we had Newton saying that time was totally symmetric. And by this, Newton did his mechanics, and he was under the impression that everything can be perfectly described as starting in one time and going to the end time according to some perfect mechanical laws of calculus, and that these laws are all totally time symmetric. So if I were to get a pendulum and I were to look at its movement in one direction, and then I were to reverse the video, it would look exactly the same. And this looked perfect, and Newton was happy with this, and his billiard balls were fine. But then, of course, the Industrial Revolution started making engines, where we've now got pistons and heat moving around, and these asymmetric behavior in time. And in this case, this thermodynamics, it shows us that when you have maybe a hot thing and a cold thing, and you start to see how your piston behaves when you heat the gas, that in general they'll become this warm mess, and you would never expect it to go backwards in time. So now we've got that time, the system starts in one state, it ends in another state, and it's never going back. And people were like a bit confounded. We're like, what's different about this process that can't be described by these balls? So like a Newtonian model of a gas might say we've got lots of particles, they're moving around, and surely I can just play that in backwards, play that in reverse, and it will look fine. But of course, this doesn't work, and people started trying to construct like this thought experiments that would kind of reveal why this process ended like this. And we see this general like theme is that these irreversible processes see this increase in what we call entropy, which is a measurement of disorder. So as time goes, everything gets more disordered, and you can't ever go back from that. And we start to have to look at like different ways of measuring energy, so that we can try and design a heat engine that will be the best. So we've got these things are getting more disordered, but what if we were to try and like trick this problem, and we were to produce, say, like a big piston with a barrier with a little hole in the middle, and we're going to put what Maxwell has been deemed Maxwell's Demon in this little hole, and he's looking at the particles in this side and those in this side, and he's only going to let them go from one side to the other, and not in the reverse direction. So we start with this system with no free energy, and sooner or later all the particles are going to end up in here. And then we put it into the piston, and we remove this work from it, and we can get energy. But of course, this is a vital problem. We don't really know what Maxwell's Demon is, but what actually does it have to do? Maxwell's Demon has to kind of remember what particles have passed through, and for this reason, like Landauer came up with his Landauer's erasure principle that says you can't erase information without a cost. So now we've got that information is conserved. So Newtonian mechanics says like energy is conserved, momentum's conserved, and now information's conserved. And what really like is information? How is it manifest? And And why then, if information has to be conserved under these laws, and we want to make a mathematical law to describe something, it should conserve everything that's within it. It has these symmetries, and it should be conserving of all of the quantities that exist in it if it's to be like analytic and true. However, we don't observe this. We observe entropy increasing, and like this is a big problem because Landau's principle doesn't describe how then entropy or how information can be conserved. Because if disorder is increasing, then information is also increasing. Because they're like two sides of the same coin. If I've got a hard drive with all of my bits of information on it, then it's either disordered to some or it's information to others. And this is the information entropy kind of relations. And information is like now a key thing to us. And recently, like Max Tegmark has been starting to talk about consciousness as more of like, well, it's not necessarily an object, a brain, it's just information in a certain structure of information that behaves like it has complex dynamics. So in light of information being an important aspect, and yet like disorder apparently increasing, which kind of is against all our notions of what physics should be. People started from quantum mechanics. The Wheeler-DeWitt equation was like this naive attempt. We make some operator that transforms a state. We call this state our initial state. And then this must equal 0. This is they just wrote this down, and they're like, great, so this is the universe. This is what time does. This is how it started, and it equals 0. And obviously, this conserves information, but it tells us nothing about what the universe actually is, because like it's very important in what way we look at it, which parts of it we're considering. And this is where the measurement becomes a really important thing in how we understand the world using quantum mechanics. So I'm going to write down this as maybe the second and only remaining equation. And it's not an equation maybe. This is a density operator, and it's how we describe things in quantum mechanics. And what's important about this object is a big matrix of numbers. It's massive, in fact. It's huge. Quantum mechanics has loads of degrees of freedom. But what happens generally is all of the classical world we understand lies on this diagonal. And this includes everything we'd ever want to describe in the classical world using Newtonian mechanics. These are all the events like this could be a probability distribution. And in general, it might just be that it's got a set of states along here, and there's a certain probability associated with each. But unfortunately, fortunately, this isn't the complete description of the world, and the world isn't Newtonian, because there are these components which exist. And this is what quantum mechanics is all about. It's about the coherences of the state, whereby some number here would be representing the interference between the state being both in this state and in this state at the same time. And obviously that's not something that has a classical analog. It's in both states at the same time, and in a way that's strictly different to a probability. So what happens, why do we observe classicality would be the important question. That's where measurement comes in. Because measurement is like something that comes and compresses this. If I come and interact with this table, I'm going to project it down onto all of the classical states, and then these observables, or these measurements I do, are always going to project me into some classical set of states. However, by doing so, I'm erasing part of the information that was contained in this, and in many ways, and by virtue of that, I'm increasing the disorder in the system, and I'm increasing in entropy. So we observe this, it's in two states at the same time, and then when I measure it, there's this randomness has been created, which is in some way an explanation of our increase in entropy in these systems, is that the small uncertainties in the gas particles are then measured by the observer, and this erases all of the necessary correlations that conserve information, and it makes it random. So this measurement process makes randomness, but that's not really, we don't like that. This is the big problem in quantum mechanics. We shouldn't have a probabilistic theory, and wave function collapse in this form is not a complete description. No one was happy about it for ages. And these kind of processes are used for like quantum random number generators and a whole load of things. But actually, we're not happy about wave function collapse. Instead, we use a different way of describing, or in larger open quantum systems, what occurs, instead of these things actually collapsing, is that we get a system so big and with so many different degrees of freedom, and these are all like little waves that spin round, that they kind of wash out. And you average over all of these waves, and you end up with a sea that, although it's many waves, it looks flat. And this is decoherence. So we effectively remove all of the necessary correlations in a system and observe what is apparent randomness. But it's only because the system's so big that we neglect a lot of the correlations. So what we want to really do is know what this is actually saying, because we never see it. Like, what's it mean in the universe? Or can we interact with it? And we recently, last year, in fact, a friend in Bristol has this new result using a certain technique whereby we can really weakly measure a system. And by weakly measuring it, we can see properties of it without perturbing it from its natural state. And what we observe when we do this is we observe like an apparent negative entropy in these coherence terms. And by having like a negative entropy, we somehow like balance up the process, we balance up the fact that the classical states seem to increase in entropy. So by doing this, or by seeing this, we can see that information is it is conserved globally by all of these coherences, but we just don't really see them. So we've got this system where like entropy looks like it's increasing because we don't see these wave-like effects because they all wash out because everything's so big. But they are there, and they maintain all of the correlations in them such that information is conserved everywhere. And the notion of information being conserved is maybe it's all right on an optics bench or in a hard drive, perhaps, but cosmologically, what can we infer from that? We start from some singularity, which has zero information. We then evolve our states under an equation somewhat like this. Maybe it's like this. It certainly conserves information. We kind of feel like that's a necessary property of a good analytic model of a universe. It's got to conserve information because otherwise it's not complete. Right? So I guess we'll skip to the end and we'll say, well, some zero entropy state is like perhaps some big spirograph. And we have a big spirograph and we look at it, and we've got the singularity in the middle, and time now takes the process of takes the form of some radial coordinate, and we exist out here where we're kind of in a local set where we can't see all these correlations, and therefore we think it's really disordered over here, but globally the universe must have conserved entropy and it must be zero entropy. So we've got this little local state that we're used to seeing, consisting of all these little bits of different bits of the world around us that look all chaotic and mental. But really, there's all these coherences that maintain like some analytic form with zero information or zero entropy. And it's kind of I mean, we can start to infer different things about what this zero information means. Maybe time is not so much a measure, or time itself is maybe more a measure of how much entropy we observe around us. This is like going from perfect order at the singularity, perfect order, and yet now by later and later times in a smaller and smaller subset of these bits, we observe this like massive disorder. So we've got time and entropy in some ways, entropy of our local universe are synonymous in some sense. And this is where we start to ask, like, what's here then? We've got a system with like finite entropy, finite information, maybe very small. Like, what's the best thing I can have with, or what's all the things that might have like 10 qubits of information. Like we start to have access to something that's far more abstract than we think the world is. Like, rather than the Big Bang beginning and being this like place where, oh well, immediately after the Big Bang there was the whole universe but small. This just doesn't make sense from an information progression point of view. There's no way I can go from nothing to everything compressed. Instead, I've got to go through this state of a triangle, or maybe I've got to construct all of the abstract form of mathematics. And I think if Plato would have known about the Big Bang when he started doing his work on what the abstract forms of things are, he would have been straight in there. He would have been like, there it is. All of maths is a physical state of the universe some earlier time, and that at the moment we're witnessing these triangles that were once existing becoming ever complexified to the point where the very triangle that I write on the board is just some fragment of a previous state of the universe, and these bits of information are all what make up our world today. So with this in mind, obviously the natural notion is, what is our mind doing about this? We've got all of this entropy going on here, all of this disorder, and it's well known that our mind's kind of aim is, it's hard, it's taking in all this information, but what it wants to do is simplify it and reverse all of this complexity into nice little abstract forms that it can manage. So whilst our mind is using up all this energy to try and order all of the information that it receives, it's kind of creating these little bits which are almost closer to some state nearer to the center here. It's almost creating these low information states within it. And I don't want to get too, I don't want to step too far through the door of what large scale correlations might exist on a zero entropy universe, or what potential for kind of interactions with other parallel states of the universe might be. I mean, we know it happens on an optics bench amongst a very small system. We can see these interactions between different states. We can see coherences, but it gives us a kind of a mechanism or a picture of the universe with which to start asking, what if the state that our mind exists in is kind of less, or is smaller and purer in some sense? And by becoming smaller and purer, these bits of information in our mind, we're in some ways less prone to the certain decoherence that large-scale systems exhibit. So where this table, for instance, would never see coherence with the two states because it's so big and these waves wash out, some small subsystem is not, it's not impossible for a small subsystem to interfere in a more quantum mechanical way, and that's what we see. And I wonder, through looking at the brain in different ways and the information structures within it, whether there are different ways in which the coherences behave, particularly like these quantum effects, when the brain and the information within it is confined and treated to be purer and of lower information state. And with that, I guess I ask you to all think about it and to maybe ask me for any references that might seem interesting to you. Negative entropies, Wheeler-DeWitt equation, and whatnot. Thank you.
Thank you, Will. That was brilliant. Incredible.